Well, welcome back everyone from your lovely spring break. Being away from your house, going to the beach, going on that lovely trip that you were planning on, all in your mind. Yes, because that's what we all got to do. Well, I hope you guys are ready to kind of get back into some stuff. I've received some responses from a few of you in terms of some work. Right now, I've been just trying to manage a lot of emails and answering emails and a lot of other background work that I've had to do. So hopefully in the next little while I can get to commenting on some of your assignments. There's a few of you. I know I've been able to make a few comments, but I'd like to be able to do some more starting tomorrow. It also looks like that we might be getting some direction from the Manitoba government and the division in terms of what some expectations are for students to do in physics. Once I have more details of that, I'll let you know. It looks like there could be an option of an online portal that the government of Manitoba hosts that students can do some physics work, and then I would be able to support you in that. It's more like an independent study type situation where there are modules that you go through, assignments that you take a look at, and then it provides answer keys. But once I get more details, I will let you know what that looks like, and if I even decide that that's the direction we want to go. So for now, we'll continue on with the way that we've been doing. I will start doing more video lessons now. I know the week before spring break I had only done one. Hopefully now I can do one approximately every other day-ish, if this is what we still continue to do. Still lots of things to kind of figure out. All right. Hopefully you've had some chance to take a look at some of Newton's second law information. Fnet equals ma, force equals mass times acceleration, and that the net force is really the combination of all the forces acting on an object. There was some textbook reading that I had asked you to do and a few assignment work from the textbook, page 93, for you to work on that. I'd like to extend now taking a look at force of gravity and being able to calculate force of gravity. So I'm going to illustrate this using an example where we have this particular question that I have up on the screen right now. What is the force of gravity acting upon a 5 kilogram ball in free fall? And it says to include a free body diagram. So when you were taking a look at free body diagrams, it asked you to sort of choose a box. Well, we can be a little more specific than that. We can choose an actual ball, and we can try to indicate that yes, we have a ball rather than just doing a box, but boxes work fine too. And so here I happen to have my ball. It's in free fall, and excuse me, if I want to do a free body diagram, I can now just indicate that I've got, I can indicate what kind of forces I have on this ball here. So in this case, the only force that I have is the force of gravity. Now this program, unfortunately, any arrows that I draw are massive. So this would be the force of gravity, and I can label this as Fg. There we go. And so that's the only force acting on the ball. And so if I want to talk about the idea of a net force being all the different forces together, then this is the only force. And really the idea when we're taking a look at net force as being all the different items put together, it really kind of looks like this. And I'm going to try to type this out for you so you can kind of see what I am talking about. So the equation that I've got here is this one, oops, right here. That this is what we're taking a look at, that all the different forces acting on an object, you just add them together in terms of the Fnet, and that's hopefully what page 93 assignment kind of showed you. So in our case here, we'll have the following. What we have is that the net force is equal to Fg, because this is the only force acting on this ball. Now, for our purposes, we happen to know what the acceleration of this particular ball is. It's in free fall, and we've already been able to establish that in free fall, anything accelerates at 9.8 meters per second squared. So we actually happen to know more information here specifically about the net force. If we can calculate this value, then we happen to know what this value is, because these two are equal. That's what this is telling us. That if we know what this value is, we know what that value is. So what can we do then to figure out the net force? Well, by Newton's second law, the net force is equal to mass times acceleration. And so we are able to put in the value of the 5 kilograms for the mass, and then for the acceleration we know that anything in free fall accelerates at 9.8 meters per second squared. So let's put those values in. So when we place in those values, the mass is 5, the acceleration is 9.8, and then when we calculate that through, and I'm going to just do this quickly the way that I normally do this. So I'll copy that and paste it, and then do like this. When we calculate this through, we will get 49 newtons. Great. So now we know that the net force acting on this ball is 49 newtons, because we have these values already from our ideas of free fall. And since the net force, all the forces combined, is 49 newtons, the only force acting on this object is the force of gravity. So now we know that the force of gravity is also 49 newtons. But this actually leads us to another idea as well. The force of gravity, it would make sense that the larger the object, more massive, the larger the gravity is going to be on that object as well. But the acceleration stays the same at 9.8. And that acceleration is due to the gravitational field of the Earth. If we take a look at the moon has a smaller gravitational force, or a gravitational field, and so it pulls less or accelerates less than the Earth would. Or if you were on Venus or Mars, those values would be different, they would be less. We go to a larger planet like Jupiter or Saturn, then those values will be more. Your free fall acceleration would be bigger. So we have another way that we can talk about the force of gravity. Really, the force of gravity, like I mentioned, is a combination of the mass of the object and the gravitational field that we indicate using the little letter g. So we can talk about that the force of gravity is equal to the mass times the gravitational acceleration that an object is experiencing when in free fall. And when we know that we're close to Earth's surface, that free fall happens to be 9.8. That's the acceleration. So there's an interesting thing then that I can do here with Fnet and Fg. I can do a substitution. I know that Fnet is mass and acceleration, and that Fg is mass and gravity. So let's see what happens if I happen to put those two into here. So what we see now is that Fnet is mass and acceleration, and Fg is mass and gravity. And hopefully you can recognize that we have mass on both sides of the equation, which allows me then to just cancel them out. So what am I left with then? What I'm left with is that gravity is equal to the acceleration. And since on Earth the acceleration is 9.8, we now have a value for gravity of 9.8. And so what we get now is that gravity is equal to 9.8 meters per second squared. So from now on, if I have a problem or a question that's talking about what the force of gravity acting on an object is, it doesn't even have to be in free fall. I can just go directly using this equation right here, as long as I have the mass, because this gravity value is 9.8 here on Earth's surface. If we're talking about a location other than Earth's surface, then obviously that's going to be a different value. But for our purposes right now, we'll always have this as being 9.8 meters per second squared. Now, one thing to note is that the force of gravity is also known as weight. Weight and weight and mass are two different things in physics. The mass of this 5 kilogram object here will always be 5 kilograms, whether we're near Earth's surface, we're in orbit of the Earth, we're on the Moon, we're on Jupiter, we're on Mars. It doesn't matter, it's always 5 kilograms. But the force of gravity will be different. The weight will be different, because this G value can change depending on where you are in the universe. On the Moon, it happens to have a value of about 1.6. So in other words, items in free fall on the Moon accelerate at approximately 1.6 meters per second squared as they fall. That means that the force of gravity is less on the Moon than it is on Earth. The weight is less. And if you happen to be in the middle of space, where there's virtually no gravitational field whatsoever, or at least not noticeable, then that means that our force of gravity is zero. You're weightless, but you're not massless. Your mass is based upon how much material you're actually made out of. Force of gravity is a vector. It always points towards the center of the object that's pulling, whereas mass is not a vector. It is a scalar. So when we start taking a look at other problems, we'll be able to take a look at that if we're asked what the force of gravity is, or if it just says what the weight is, as long as the mass is given to us, we can use the value of 9.8, and that can give us the force directly. So the equation that I happen to... Alright, let's take a look at another question here then and see if we can apply this. What is the weight of a 2 kilogram hedgehog? I just decided hedgehog because, we talked about, what was it? Pandas. I think we had a question about penguins at one point, maybe? I don't know. My kids have been obsessed about penguins, so maybe I'm just thinking that we did a question about penguins. Anyway, 2 kilogram hedgehog. Can we figure out the weight now? Can we even do this if the hedgehog is not in free fall? The question doesn't tell us if it's in free fall or not, and right now it doesn't matter, because we have a method of figuring out the weight, the force of gravity, just based upon this mass. Since there's no other information given, we're going to assume that this is going to be near Earth's surface, so we can use the value of 9.8 for G. Here I've got a picture of a hedgehog, and we want to know what the force of gravity is, or the weight of this hedgehog. So I've got Fg equals mg, and now I can place in my values into the equation. The mass is 2. Gravity has a value of 9.8. And so when I calculate this through, we get that the force of gravity, hopefully you guys can recognize what this will be already, is going to be 19.6. Oop. I forgot to do like that. There we go, 19.6. And because it's still a force, we will measure it in newtons. There we go. And so if I want to, put a box around that, because I've always told you guys that you should put boxes on it. Like this. Let's see if I can do a box. Oh, triangle. What the? I don't want a triangle. That's not a box. Let's try this again. Oh, it tries to recognize what I did. Ooh, look at that. Dun da da da. Sweet. So, what is the weight of a 2 kilogram hedgehog? 19.6 newtons. So, now we have a method to figure out what this is going to be. All right, let's take a look at another question here. Type this one out as I go. This one we're not going to focus on weight now. We're going to focus on just Fnet equals MA. Conrad is pulling a 30 kilogram sled with 300 newtons. Kevin is pulling the same sled in the opposite direction with 500 newtons. Draw a free body diagram. Oops. And what is the acceleration of the sled? Nice. Okay. So this really means that, we could think about left and right. It doesn't say if Conrad is pulling left or right, but we do know that Conrad and Kevin are pulling in opposite directions. If you think about the scenario, it doesn't make sense that they're pulling up or down unless that's specified. So let's just think about it left and right. Let's draw a basic sled. I will just draw a box for my sled. See if it recognizes. There we go. There's my box. And, excuse me, I need to draw a free body diagram. Okay, so now I'm going to try to get my arrows here. And again, these arrows are always really super huge. Let's see if I can make them a little smaller. So we do have Conrad pulling one way. Let's say Conrad is pulling this way right here. And I'm going to call that F1. Alright, so we're going to call that F1. And then Kevin is going to be pulling the same sled, but in the opposite direction, like this. And we're going to call that one F2. Okay. Now, one of the problems here is that we see that Conrad is pulling with 300 newtons and Kevin is with 500 newtons. So really, this force here needs to be bigger than this force here. So I'm going to adjust this force here and try to make it a little smaller so that it's more obvious that this one here is bigger. Now, technically, there are two more forces acting on this object. Can you guys figure out what they are? Well, one is going to be the force of gravity. And I could figure out what that is, because it does give me the mass. But it doesn't ask me to do that. The other force that is acting on this is the force that is preventing the object, the sled, from falling through the ground. And based upon some previous reading that we had done, hopefully you recognize that's called the normal force. And the normal force is always perpendicular to the surface, so in this case pointing up. And because the sled, it doesn't make sense for the sled to accelerate down or up, these two forces, the normal force and gravity, they're going to have to cancel. Let's label these. This one here is Fg, and this one here is Fn. There, that's a bit better. So even though this is the correct free body diagram, these two forces here, they're going to cancel each other out. And so eventually we're going to notice that we don't have to consider them, but this is the correct free body diagram, and this force is larger than this force. So we should already get the idea that this sled is going to accelerate this way. So let's take a look at some of the equation work that we can do to figure this out. So the net force is the combination of all the forces together. And in this case, we technically have 4 forces. But, like I said, these two here cancel each other out. So we only have to really consider 2 forces, this one and this one. Now, because these 2 forces are acting in opposite directions, it makes sense that one of them is going to be positive and one of them will be negative. Let's call this force here the positive one. This is the one that Kevin's pulling with 500 newtons. And this one here is the one that Conrad's pulling with 300 newtons. So, let's see how this equation then looks. What we get is that Fnet equals F1 plus F2, because these are the 2 forces that we're talking about. We can now substitute in values, and so we get that the force that Kevin is pulling is, oh sorry, we wanted this one positive. Let me quickly change that. There we go. So what we've got now is that Kevin's pulling 500 newtons, that's this force, and Conrad is pulling in the opposite direction of 300 newtons, and that's this force here. So we know already that we're going to get a total of positive 200 newtons. Great. Now what this allows us to do is to use our Fnet equals MA equation. Alright, so I've got the Fnet equals MA here. Fnet we just figured out is 200 newtons. We have the mass of 30, so that's going to allow us to figure out what the acceleration is. We'll put in these values. So our Fnet will be 200. Our mass is 30. And we have our acceleration. And so now when we're going to figure out what the acceleration is, hopefully you can recognize that I've got to move the 30 over to the other side. So I'm going to divide both sides by 30. And I'm going to get that the acceleration is going to equal 200 divided by 30. And 200 divided by 30 gives us 6.6 repeating. So let's round that to 6.67. And the unit, of course, is meters per second squared. There we go. Let's see if I can get my box for this. Excuse me. Nope, not arrow. That's not what I want. Nope. Let's try that again. And blink. There we go. Okay, so I hope this is going to be helpful for some things for our next assignment. I'll be assigning page 97, numbers 15, 16, 17, and 18. Try to figure them out. Make sure to draw free body diagrams. It may feel a little simple at this point, drawing them out, but it's actually a very, very important skill to get into as you move forward with more and more of this physics and as we get into more and more complicated problems. Hope you guys are doing well, and we'll talk to you soon.